Thank you very much for the kind introduction, and thank you for inviting me. I'm glad to discuss a little bit of an overview of machine learning and energy physics with everyone today. Please interrupt me if you have any questions, and I think we'll probably cover some ground that you covered in some of the other lectures, but hopefully there's some new insights or connections to be made. Right, so why don't we jump right in? So first, I'll sort of start off with sort of thinking about what we know. So what we know in high energy physics is certainly quite a lot, at least about the matter we see around us. We sort of know that we know the sort of building blocks of leptons and quarks, how forces are carried between particles, and the new Higgs boson that we discovered, giving mass to the other particles. And we actually we of course know the Lagrangian of this theory. We know quantum field theory. Sort of this equation here on the right, we know how these particles interact and their dynamics. And the key here is this is really a predictive model. So it's a predictive model in the sense that we can use it to make predictions about what will happen at experiments like the LHC. And here on the bottom left, I love this plot. It shows 14 orders of magnitude of predictions of the rates of different processes, the different processes on the x-axis, in the comparison in theory with the gray bars and experimental data in different colors with, sort of fantastic agreement. And the fact that we have this this predictive theory will sort of come back when we start thinking about how we do data analysis at the LHC. And of course, at the LHC, which is where I primarily work, and we're basically going to be talking about collider physics here, right? We care about trying to ask the questions beyond the standard model. What is the nature of the Higgs boson? What is dark matter? Why is there a matter-antimatter asymmetry? And we can use tools like the LHC to do that. So we perform 40 million collisions a second, extracting data from, I work on the ATLAS experiment, large experiments with multiple layers of detectors. Maybe you're all familiar with this. And I think one of the ideas here that's quite important is, we have to collide particles many, many times a second in order to accumulate statistics, because some of these processes are very rare. And we can't say with certainty that any single collision is a given type of interaction, but we accumulate populations and we compare and study populations of events. That being said, we still have to understand how to describe what's happening in any given collision. So we have to study collisions. So in studying collisions, we have events like this. This is just in case there's any people that are not studying collider physics here. I wanted to go through this a little bit. If they were studying a different type of high energy physics. Right, so in this top left is a cross-sectional view of ATLAS where the beams are coming into and out of the page and colliding at the center. And you see these particles coming out. These purple curves are charged particle trajectories. We don't see the neutral particles because they don't interact with, these are silicon detectors, basically digital cameras, collecting charged particle energy depositions. And then everything slams into the calorimeter here where we get energy depositions in sort of the green and red region, and the histograms represent how much energy there is. And in the bottom, you can sort of see a side view where the beams are coming from the left and right. So we get data like this. This has already sort of been pre-processed because we've drawn where the particles go, but really there's lots of little dots here you can sort of see. And so what we have to do to study these collisions is figure out what exactly happened here. And so I'll give sort of one example of kind of the kinds of questions we ask reconstructing particles. So if you had something like an electron, it would pass through multiple layers of silicon detectors, leaving little energy depositions here on the bottom, and then smash into the calorimeter and stop, leaving some energy depositions. And so the types of things we need to do to develop algorithms to do are to cluster together these energy depositions. So figure out what's in the calorimeter is related or cluster together these energy depositions in the silicon. And then given this sort of set of data, we have to ask questions like, is this an electron, right? So that's sort of asking the question, what's the probability that this data gives us, that this is an electron given this data? And if we believe we can classify this data as an electron, then we need to start solving things like regression problems. Okay, so given that we believe this is electron data, what's the probability of this underlying electron that created this energy signature in the detector, that it actually has some true underlying energy? And so those are the kinds of sort of tasks that we end up needing to ask. A lot of things in terms of classification and regression and clustering of data. And we develop algorithms for each kind of particle, and ultimately we start to think about events a little bit like this, where here's some collision, but actually there was two bottom quarks that created jets here. So those are collimated streams of particles created from high energy quarks and gluons, and we'll come back to that. And then you have things like muons that pass through most of the detector and leave signatures on the outside, or electron here, or a neutrino that doesn't interact with anything but shows up as an imbalance. And so we can sort of document all the different particles in these events. But we have to sort of, ask, well, how do we actually build up these algorithms? And then, okay, once we find these particles, what do we do with an event that has some number of particles in it? How do we then go and start to extract information about collections of events, about asking questions about, for instance, the standard model or new physics from these events? And for that, we can think a little bit about the data generation process. So we know a lot about how data is generated in collider physics. So starting from the sort of standard model, which has roughly sort of 20 free parameters, and maybe we'll add more if we add sort of in a theory of new physics. From there, we can calculate Feynman diagrams, which are basically hard scattering probabilities that sort of tell us what's going to happen at the hardest scattering of this event. In this case, I mean, this example produces 2 top quarks and a Higgs boson. But those particles aren't quite stable, and they evolve, producing around, on the order of 100 stable particles in a collision that have gone through sort of the showering and hadronization process. And these are stable in the lifetime of the detector. But this still isn't what we see. What we actually see is those 100 particles smashing into the roughly 100 million detector elements of the detector. And so this is sort of where the problem begins to arise. The problem of sort of doing statistical analysis at the LHC begins to become quite relevant. So we want to ask questions about the fundamental parameters of the physical model, of the standard model, for instance. We'll call this theta, but we only have access to these 100 million detector elements. And I don't think anybody knows how to compute the probability of these 100 million dimensional events given some parameters of the standard model. Effectively, we'd have to calculate the probability of all possible intermediate states, all possible collisions that could have given us this detector signature. And these are very, very complicated processes. So it's a fundamentally stochastic process. It's very high dimensional, and we can't actually compute how likely anything is. But what we can do is simulate it. We have a mechanistic understanding of each of these pieces. So we can simulate these processes to develop simulations that allow us to then build algorithms using simulations where we know what's happening, where we know what the answers are. And eventually we'll see we use these simulations actually to do statistical inference. And so you can sort of think of the data analysis process as the inversion of this data generation process. So starting from these 100 million detector elements, we're going to try to reconstruct particles, roughly what was stable on the lifetime of the detector, electrons, charged hadrons, maybe even grouping them into jets. And then from there, we sort of look at these events and try to select interesting ones. If we were looking, for instance, for a TT bar Higgs event, we'd be looking for multiple bottom quarks, maybe electrons and muons. So we try to then select and identify interesting events with the same signature, maybe reconstruct the top quark by adding together particles that we have observed. And from there, we get collections of events that have passed our selection that we think are signal-like for whatever we want to study, and we can perform statistical inference, basically measuring values and confidence intervals about in terms of the parameters we're interested in. And so this is sort of how then statistical inference at a very high level works at the LHC, right? We have experimental data that we're going to pass through some data analysis chain that we've developed this data analysis chain most likely using simulation to tell us how to develop these algorithms. We also then pass our simulations through this data analysis chain as well with some parameters. And that allows us to, by comparing experiment and simulation, we'll be able to estimate some value of these parameters. So we get some, we perform some statistical inference on the parameters theta. And so how do we actually do this? Well, we don't know how to also, at this point, or we'll see some new ideas with machine learning, and I think you've heard about some of them already. But for the most part, up to now, what we do is we can't analyze 100 million dimensional data for each collision. So instead, we simplify that information. We compress it down to what's usually one informative number. So for instance, in a Higgs boson analysis, if you're looking for a Higgs boson decaying to 4 electrons or muons, you might compute the invariant mass of those 4 leptons. And this is the distribution the number of events on the y-axis and the value of the mass in a given event on the x-axis, and you can make these distributions, basically histograms, where we can very easily compare simulation and data in one dimension. So here the simulation is in red and blue and the data is in black. Now this histogram serves more than just giving us a visual cue. It's telling us the expectation from our theory. And because we've histogrammed it, it also tells us effectively how many events we're expecting in each bin. We can develop a Poisson likelihood model based on these histograms that we can then use for downstream statistical inference. And so that's sort of how we compare simulation and data in order to then do statistical inference, usually frequentist statistical inference, and extract values of the parameter theta. So then what kind of goals do we have when we're doing this kind of data analysis? Well, there's many. We sort of talked a little bit about physics parameter estimation. So sort of in this, the top right example is measuring the rates or the cross sections of two different Higgs processes. We might want to do hypothesis testing. So in that figure from before, is this data consistent with there being a Higgs boson or not? We might want to compare measured distributions to theory, sort of when you do things like unfolding, which I think you heard a bit about. When you unfold data, now you can compare your measured data to theory to see if you understand things like QCD physics or electroweak physics. You might want to then tune a simulator to better match data. And as we'll talk about a little bit at the end, we can even start thinking further using simulations to help us design and optimize future experiments. So that was sort of high energy physics or collider physics from a bird's eye view. And then we could ask the question, well, what do we want from machine learning and high energy physics? And I think there's a variety of places it's shown up. We certainly care about complex pattern recognition. We have these complicated detectors. We have to figure out what's going on in them. We're going to want to try to avoid or improve that issue of compressing all the data to one dimension, find high dimensional ways to do statistical inference to improve our measurement precision. We might want to be able to better search for new physics signatures as we search for signs of beyond the standard model things happening in our data. And another one is actually trying to reduce resource demands. So this is a figure as a function of year of the amount of compute, CPU compute needed by the CMS experiment. The gray band is what's expected to be available. The blue on the top, the solid blue line, is what the computing resources that would be needed without any additional R&D, sort of falling outside of the region of what we believe would be available. And so additional R&D or improvements are needed to get down to this dashed line, which keeps us within the safe region. So we need improvements in our computing in the algorithms that we develop to stay within the resources that we expect to have available. And so I like this quote. It's used a lot, but I like it. It's from Freeman Dyson. New directions in science are launched by new tools much more often than new concepts. And I think machine learning certainly falls into the category of a new tool, although it's been around and sort of growing in the last few years. I think there's still a lot of new ideas developing, in fact, new directions where machine learning is beginning to help us address sort of new challenges. And we'll try to talk a little bit about that today. So I think it's exciting to have machine learning sort of infusing itself into the high energy physics data analysis workflow. And I think it's effectively at this point infused. We have machine learning infused everywhere in our data analysis chain, everywhere from how we take experimental data, where we'll see a little bit about low latency or fast machine learning, in simulations where we try to speed up simulations using machine learning tools. Reconstruction, certainly there's a lot going on in pattern recognition, trying to find particles better in our detectors. And also statistical inference, where we're trying to do things like, figure out, estimate parameters like the masses or cross sections of particles. Okay, so we'll jump into the first. We'll sort of go through each of these categories, not in this order. But we'll sort of go through each of these categories yeah, so that's the plan. So pattern recognition and model development, I think, so certainly data at the LHC and in colliders is quite complex. It's very high dimensional, as we've already discussed, but it's also quite sparse. In a given collision, there may be on the order of a few hundred particles. So, but they won't sort of deposit energy in all of these 100 million detector elements. In fact, they'll deposit energy pretty sparsely. You can see just a little bit mostly empty. And so we need tools that can deal with the sparsity of our data, the high dimensionality and the fact that it's quite irregular. It's not data that's organized on a simple grid like in an image. We have to deal with the irregular geometry of these detectors. And sort of, I think there's been a lot of development in the machine learning for high energy physics to try to figure out what's the right way to think about our data, what's the right way to represent our data, and thereby determine what are the right tools to be using. And I think there's been quite an evolution, starting back from images, where we were thinking about, slicing out pieces of the detector, like the calorimeter, and treating them like images and using computer vision and convolutional neural networks. And that's certain first trying to think, instead of about slices of the detector, thinking about the particles we reconstruct, but as a set, or actually in the beginning, we were thinking about sequences of particles. Because those tools were actually what were available. So thinking about a set of particles as a sequence to process them with recurrent neural networks. Eventually, set-based tools sort of came into existence, and we were able to use set-based tools to avoid any sort of random determination of how to order particles. And ultimately, I think today, most of the tools we build are built around graphs or transformers, which can also deal with sort of set-based sets of particles that don't necessarily have any inherent order. Right, so so we'll talk a little bit more about graphs in the upcoming slides. I think you've probably learned a bit about graphs, but here's the quick overview. In a graph or a graph neural network, you have a series of nodes. Each of these letters and circles is a node, which, for instance, would be a particle, and it would carry information about each particle, its energy, its momentum, maybe its impact parameters. And then you'd build a graph based on some either known information or a heuristic. Maybe these are the nearest neighbors of each of these particles, here represented by edges. And in a graph neural network, you can actually perform message passing, which is to say that you receive messages from each of the neighbors or anything connected to a given node here in the center. And that information is typically processed through a neural network. Everything can be added up or processed by another neural network to tell us how to update the given representation of a node. And so that same process is repeated for each node here. So it's sort of like moving a convolution around, but on a graph instead of on an image like you may have seen in convolutional neural networks. But this is a very powerful paradigm because these nodes don't have to represent any regular geometry. They can be placed, they can be related, they can be anywhere in space and related, for instance, through their distances. There can be a variable number of them. And if there's lots of zeros in the detector, it doesn't matter because we can, for instance, only put the information or the detector elements where there is information into nodes in the graph. And so as a result, these graph neural networks are very good for the sparsity, irregularity, and variable cardinality, the variable number of particles or detector energy depositions we see in a given event. And as a result, they've been used quite a lot across tasks. So for instance, in tracking, which is basically playing the game of the connect the dots, we have energy depositions here in red in a silicon detector, and we need to figure out which one of these are actually particle trajectories. We can do similar games or build similar tools in the calorimeter. Sort of once we see energy depositions, we can try to analyze that cluster to determine what are the underlying properties of the particle or what kind of particle created that that energy cluster in the calorimeter. We can classify jets, and we'll talk more about that, which is effectively classifying what heavy parent or what parent particle created these streams of particles. And we can even classify events. So, once we've identified a bunch of things, we can say, okay, this event has 2 jets, a lepton, and missing ET. We can build a graph of that event and then try to process it to classify whether it's from a new signal or not, for instance. And so we'll focus here the discussion mainly on classifying jets. That's effectively sort of the canonical discrimination challenge. It's actually a good introduction to a lot of the machine learning we do. A lot of people get involved in jet classification as a first introduction to machine learning in HEP. I think it's a place where we probably made some of the most progress in any of the machine learning applications, partly owing to the fact that we've been working on it for quite a long time. So here, what we're trying to do is we have these collimated streams of particles on the top left. These are each of these different colored collections are, for instance, a given jet. And we want to classify whether that, for instance, came from a light quark or gluon, or maybe something heavy like a W-Rizzi boson, Higgs boson, or top quark. Now, these other particles, these heavy particles, when they're boosted, when they have a lot of energy, their decay products overlap, and we get interesting and complex internal substructure that can allow us to sort of discriminate between these different kinds of particles. Now, we're not going to go through each and every different kind of architecture. What I really want to emphasize is the fact that this evolution of thinking about different architectures and moving from image-based tools to graphs where we can incorporate both the fact that they're variable length sets, we can incorporate particle level information, and we can incorporate their sort of relationships to each other, be it, for instance, how close they are to each other, their distances, gives us a lot of power. And in fact, if you compare, there's a nice paper, this is from 2019, but it's often updated, trying to classify top quarks from quarks and gluons. And pretty much at the top of that list for a long time was this model called ParticleNet, which is basically a big graph neural network where you'd pass in all the particles, process the neural network with a bunch of graph convolution or graph message passing layers, and then try to classify whether this is a top quark or not. You can see that actually what's interesting, look at some of the other models like convolutions, they actually do quite well. And many of the models can actually do quite well. And in fact, if you look at this, this is sort of a ROC curve with the true positive rate, or the efficiency for tagging top quarks versus the rejection on the y-axis, or 1 over the false positive rate. So top right is better. A lot of the models tend to sort of collect around a rejection of, close to 500 or 1,000. The difference in many of these models, though, is, for instance, parameter count. Some of these convolutional neural networks take 3 or 4 or 5 times more parameters to reach the same efficiency or same performance. Now, in the past, we said that that was a problem. Now, of course, we know from a lot of the modern machine learning that scaling up models is something that people think is quite useful. So understanding the balance of scaling models up, I think, is an interesting future question. Nonetheless, even with these differences in scales, 3 or 4 times bigger convolutional models, the graphs tend to do better. And we also have a few models that tend to do quite well with quite a few very small numbers of parameters. So in this case, it's called the tree network. We'll see that it's actually a neural network that's organized around the structure of the way the jet is processed. And I'll explain that a little bit more. But the idea is we're using more physics information that allows us to actually gain quite good performance with very few parameters. It's actually something that happens a little bit on the right-hand side as well. The top blue, the red curve here is the graph neural network. And the top blue curve is actually a graph neural network that has additional information input to it, actually additional physics insights, which is adding symmetries to the model. So what do I mean by these two models where we're sort of adding physics information? Well, in the first one where I was talking about this tree network, what you see here is this sort of tree, and you can imagine that each of the leaves at the very bottom is where we'd put the information about a given particle. But then the way each of these nodes represents, for instance, a small MLP, a small number of neurons that do some processing, the way that the information is processed is by combining information from multiple particles or from multiple branches along the structure of the jet clustering history. So we found a jet by running some jet clustering algorithm, and we can use that jet clustering history to organize the structure of a neural network to try to process that data. And this works quite well. Very few parameters are actually needed, at least to achieve quite strong performance. And we think there's a lot of physics information that we put into this model organized around the way that we think, for instance, particle splitting and showering happens. On the other side, we saw models that had symmetry in them, so specifically Lorentz symmetry. So the idea being, if you boost models or boost particles or rotate them, they're still the same particle. Our model should be insensitive to those boosts, and that's the kind of information that you can add into these models. And there's been a lot of work trying to figure out how to add these kinds of symmetries into neural networks. And I think these are two really interesting examples that begin to point towards an interesting question of how much should we be thinking about or building the next generation of our models in a more sort of hybrid physics AI approach. So we have our sort of traditional approaches, the sort of pre-machine learning era where we would think hard about the physics. We would think about interesting variables in the jet context and maybe substructure variables. And we would compute those to try to separate and classify different kinds of jets. At some point, we even began putting them all together, sort of using these high-level features and decision trees and neural networks, and that works reasonably well, not as well as some of these other, for instance, graph models we saw. On the other side, there's sort of the full machine learning picture where we sort of try to fit our data into some machine learning approach and then just process it with lots and lots of data. and it's sort of very data-driven with minimal assumptions. And that sort of fits on the other side of a full machine learning approach, but maybe there's something more in the middle where we think about how to incorporate our physics knowledge. For instance, we saw examples of symmetries. We saw examples of structure. The jet clustering history was sort of the structure in the model. We can even think a little bit about compositionally. If it's a more complex task, we may want to compose it into subtasks, and rather than sort of going from starting from a detector hits and then classifying Higgs bosons, we may want to do things in the middle like find particles. And I think you even had some lectures on differentiable programming where we can start to think, okay, well, we have physics code that implements some algorithms or, for instance, some dynamics like equations of motion that we could actually use inside of our machine learning models. And I think there's a lot of interesting questions about how far we can push or how much we can benefit from these kinds of hybrid approaches. So I'll just talk a little bit about multi-component systems because I think there's been some nice progress there. So here's two examples. One is an AI agent playing the game of diplomacy, and on the right-hand side is a robot that's being run by an AI agent. And in both of these cases, the agents have multiple components. So they have components to speak to other agents in the system. For the robot, it's, for instance, speaking to a human. The human tells the agent what action it should perform. It then processes that information to determine an action. It then has a computer vision module that allows it to see what's in front, interpret the action, and take action. And then it still has to determine whether the action was successful or not and make a decision about what to do next. And so there's actual multiple pieces, a language piece, a vision piece, a sort of a sequential decision-making piece that all have to fit together to build these models. And they're sort of structured around the way you'd sort of think a human might go about this task. Understand the request, understand what's in front of you, understand the context, and then think about or create a process about how you're going to go about achieving that task. Now, we don't have quite the same level of reasoning in our tools, but we do have multi-component systems. Here's an example of some of the work towards building graph-based neural networks for tracking. Now, this isn't one graph neural network. It's actually a multi-component system. So given some hits in the detector here represented by a blue line, and this is supposed to represent a cross-sectional view of the XY plane, so the beams are into and out of the page. We start with some hits. We first have an algorithm for constructing a graph. Then there's a second algorithm or second model for trying to classify edges on that graph to see whether they're good edges or bad edges. And once we've sort of figured out which are the good edges and bad edges, we have to identify connected components and turn them into which of these connected components is one particle or another. Effectively, which part is a track and which isn't a track. So this is quite nice to see. We're beginning to build more complex models that can sort of achieve different tasks, and they're built around the knowledge we sort of have about how we would typically go about doing tracking, but where the pattern recognition is now done by a more complex tool. Similar ideas are being addressed or being thought about in particle flow. So in particle flow, we want to be able to identify which energy depositions in a calorimeter belong to the charged particles in an event. And then from everything that's left over, we want to figure out, which are the neutral particles. How do we identify all the different particles, combining the charged information from the tracker with the sort of calorimeter where we don't, everything's mixed together. And there's been some nice work thinking about how to put all this together in large graphs and process, entire sets of particles and try to sort out from this graph, what is the list of charged and neutral particles. And so you see a very similar kind of breakdown where there's, in these kinds of models, there's a graph building step where you sort of take all the hits that you have in the tracks and you build them into a graph using some relational information like nearest neighbors. Then you try to cluster information together, figure out which components you think are related to each other. And with those clusters, then try to start thinking about particle prediction. Okay, so given this clustering together in the graph of information, what kind of particle produced it and how much energy did it have? So it's again sort of broken down into sort of very reasonable or understandable components where the pattern recognition is done by something more complex like a graph neural network. So I think these are very interesting, and it's allowing us to tackle more and more complex challenges. We're going to have to deal with how to scale these models up. A lot of these, for instance, either focus on small parts of the detector or, for instance, have data rates that are amenable to run 3 of the LHC, but when we get to the high luminosity LHC, there'll be many more collisions per bunch crossing. The data rates go up, and so too do the algorithm runtimes. This is the algorithm runtime versus how many pieces of information are in the detector that has to be processed. There's a lot of discrete information that happens in some of these more complex tasks. Like we talked a lot about clustering. Well, clustering eventually has to make a decision. Is this particle part of, or this information, this bit of data part of cluster A or cluster B? And that discrete decision is not really differentiable, at least not naively. And so we can't easily optimize all these systems together or optimize through a clustering step. How do we calibrate these models? How do we make sure when we build these models from simulation that they're actually going to work well in data, or that they're tuned to the data efficiencies? And there's actually been some nice work to think about how to even do high dimensional calibration directly in the data with things like optimal transport. I sort of mentioned this, but from the optimization perspective, once we're starting to build these more complex multi-component systems, we have to figure out if we're going to jointly optimize all the pieces, or fine-tune them, or optimize them separately, and how we design losses that ensure that we sort of can achieve each of these intermediate steps successfully. So I think there's a lot of open questions here. So if you're interested in these pattern recognition tasks, there's certainly quite a lot to do. But we're going to sort of move on to another topic, although a related one, on pattern recognition at low latency. So data acquisition is sort of what happens before we do a lot of the sort of offline data analysis. And we collect enormous amounts of data at the LHC, but actually we throw out most of it. From the sort of 40 million collisions per second, we only keep about 1% of it on disk. And in order to do that, we have to run algorithms to figure out which is that interesting 1% and which is the other stuff that we can discard. And so there's sort of a multi-step process of, hardware-based level 1 trigger, basically algorithms put in electronics to pare down the data from 40 million to about 100,000 collisions per second. And then we pare that down again to about a kilohertz of rate using CPU-based algorithms. And so an interesting sort of question has come up or been addressed, which is, we've got all these great machine learning algorithms for doing pattern recognition. Can we improve the trigger? Can we put better algorithms processing faster on CPUs or potentially GPUs? But we'll talk a little bit on the next slide about how people are starting to think about putting these algorithms in hardware directly. So more specifically, there's been a very nice community-led effort called HLS4ML that sort of deploys neural networks as an electronic circuit on hardware. We're basically going to put the whole model on a chip, but now you have all sorts of interesting new challenges, which is not only how do you make a highly efficient model, but how do you also make sure that it fits on your chip with your resources available? So how do you compress models? So I think you've already been doing some HLS4ML tutorials. I think these are really interesting tools. Here's an example on the right of some work we did trying to compress or get recurrent neural networks, so sequence-based models to run on FPGAs, where as you examine the number of bits you use to store weights and data information, you can see how many resources are used, and that's sort of part of the optimization. So I think these are quite interesting tools that will have a big impact on future trigger systems. And even I think now some of the first HLS4ML models have already been deployed on CMS. Right. So now we'll move on to the next question of resources. So can we also begin to sort of reduce the amount of resources we use? And certainly simulation is one of the biggest users of our compute resources. More than half the computing resources on the grid are expected to be used by Atlas. It's an enormous fraction of our compute, at least as predicted from now. And as we sort of saw, this is the similar plot you saw on CMS. Now this is Atlas, where unless we reduce our CPU consumption, we'll actually be outside of the bounds of what we think we might reasonably have available to us, for the high luminosity LHC. A lot of this is driven by the fact that the HLHC will have a lot of pileup, and the compute demands will be quite heavy. So one of the approaches to this is to build generative models. So a generative model is a probabilistic model, which I'll call Q here, that's used basically as a simulator of the data. So the goal is to generate synthetic, realistic, high-dimensional data. So here's the simulator, at least the distribution of data that the simulator represents, and it can generate data points. And our goal is to make the data that we generate as close as possible to the unknown data distribution, or the unknown distribution that the data follows. So we only have empirical samples from the data, but we want to try to make our synthetic data as close as possible. And there are many tools to do this. We're not going to go through all of them. You may have heard of some generative adversarial networks. We'll see an example on Atlas in the next slide, but there's also variational autoencoders, normalizing flows, and these days, sort of what's been doing a lot of the heavy lifting is diffusion models. Now, the thing I want to sort of get across is you see in each of these models, there's this red square that denoted Z. So that red square is basically a simple noise distribution. Often it's Gaussian. And so in each of these models, the way that they're built is we're going to sample some noise, some simple noise, and then we're going to transform that into the data using a neural network. Now, the way that we actually do that depends on the model and depends on the constraints, but effectively the whole idea here is we sample random noise in a simple distribution and use a neural network to turn that into something that looks like data. So in a GAN, we have a second neural network to try to tell whether we've done a good job or not. In a variational autoencoder, we try to predict the value of Z. We use a sort of a posterior inference challenge. In flow-based models, we constrain this transformation to be bijective, so invertible. And in diffusion models, we actually iteratively add noise and then iteratively denoise. It's actually sort of an iterative sequential variational autoencoder. But we don't need to get into all of the details. The idea is we turn noise into data with neural networks. And this can actually do quite well. So one of the biggest challenges for the collider experiments is the calorimeter, basically how particle showers occur, because, like an electron, when it hits the detector, breaks into many, many particles or splits into many particles to deposit energy and create a shower like you see on the bottom left. And so we can actually train, in this case, GANs, generative adversarial networks, to try to mimic GEONT so that we could speed it up. And in fact, that works quite well. This is the CPU time versus the energy of a given photon, how long it takes to simulate a photon. And you can see orders of magnitude improvement from GEONT down to these fast simulators. The red here is the neural network or the GAN approach. So it works quite well in terms of reducing CPU time. And in terms of accuracy, well, it's quite good. So this on the right-hand side is the momentum of the photon versus sort of the ratio of the observed to true momentum, basically the fraction of energy that we observed. And you can see it's very nicely matched both in mean and variance or standard deviation here between GEONT in black and the fast calorimeter, basically the neural network here in red. And so it's actually doing quite a reasonable job of producing accurate simulations for these kinds of photons. But it can always be improved, and these are some of the challenges, which is how do we improve the fidelity and flexibility of these models to be able to, simulate over wider ranges in different parts of the detectors at higher fidelity. And another major challenge is how we validate them. So you might think it's very similar to validate, this is just another simulator, we can validate it like anything else. And I think to some level that's true, but sort of fixing these models as we see problems is a little more complicated because they're not as interpretable. It's harder to deal with, or it's easier to think about, we understand this splitting process is wrong GEONT than if everything is done through a GAN. Nonetheless, there's been great work on understanding how to validate these models and estimate uncertainties when we think they might not be doing a great job. And so this is also kind of interesting and difficult work to make these models more and more usable and powerful for future implementations. We also see deep generative models moved in event generation, basically sampling from the matrix elements, often using normalizing flows, and they can actually do quite a good job of getting good fidelity on sort of high fidelity matrix elements where you have lots of particles. And this is sort of important because matrix elements with lots of final state partons can actually be quite inefficient to sample. So being able to speed that up can really improve our sort of Monte Carlo efficiency in the future. So we've talked a bit about simulation, and certainly simulation is used in our inference, but we're gonna sort of move over and think about that last challenge we mentioned before, which is how do we improve the way we actually extract information from our data, our statistical inference? And we'll see a little bit also of how can we start to do new interesting things using machine learning for inferential tasks. So we started with this picture where we start with sort of 10 to the 8 measurements in a detector. They get summarized down to sort of one feature, and we make the distribution using lots of events. And comparing these histograms, we can do statistical inference. And we have to do this because we have no idea, for instance, how to compute the probability of this collision given the theory parameters. But 100 million to 1 is sort of a pretty big compression. So can we avoid such a large compression? Can we use more information from our data? And that sort of broadly fits into the picture of what's called simulation-based inference. So simulation-based inference is using simulators to estimate key statistical quantities. So specifically, either estimating likelihood ratios, which, for instance, you need for frequentist statistical inference, or posteriors, which drives Bayesian inference. And so the idea is you can generate lots of samples with your simulator, and you want to be able to estimate one of these statistical quantities that you can then evaluate on your observed data. So there's lots of techniques that depend on, how high dimensional your data is, how costly it is to run your simulator. Histograms sort of fit on the bottom. We can't really do high dimensional histograms, but nonetheless, there's lots of other techniques, and we're going to focus almost exclusively on the likelihood ratio estimation, because that's sort of what we use for frequentist interval estimation in collider physics. So the broad picture that happens when we use neural networks here is, sort of we take our simulator and we generate lots of data, and then we might have a prior distribution if you're doing Bayesian inference where you sample different values of the parameter. Or if you want to learn a likelihood ratio for different parameter values, you might even have a proposal distribution that helps sample different theory parameter values. And then you'll basically use a neural network to learn either a likelihood ratio, a likelihood, or a posterior. So these bottom two are often done with normalizing flows. We're not really going to get into how that's done. We're going to talk more about likelihood ratio estimation here on the top. Nonetheless, once you've estimated this quantity with a neural network, so the neural network, you, for instance, feed in data and the parameters that outputs a probability, then you can then use that, or probability ratio, my apologies. Then you can sort of feed in the measured data into that model and perform statistical inference, so estimate posteriors or confidence intervals. So likelihood ratio estimation actually comes up a lot. So even in Bayesian inference, where you need to compute the ratio of the likelihood to evidence, so this is P of X given theta over P of X, where you've integrated out theta, that comes up for posterior inference. Also in hypothesis testing, where you want to compute the ratio of likelihoods under two different hypotheses, here being different parameter values. Or you might want to sort of compare a complex hypothesis, a set of thetas, to a null hypothesis, as is often done in hypothesis testing. Now, what's important is we know the reason we want to do this, at least in frequentist interval estimation, is we know the most powerful summary statistic to decide between two simple hypotheses from the Neyman Pearson lemma, and that is the likelihood ratio. So the ratio of the likelihoods of the data under two different hypotheses or two different parameter values. That test statistic is going to be the most powerful one we can for doing things like interval estimation and hypothesis testing. And what's sort of interesting, and the reason why we care about this in the machine learning world, is it turns out we can estimate this ratio without knowing the numerator or the denominator. We don't need to estimate the likelihoods of the data. We can estimate the ratio directly. And that's done using what's called the likelihood ratio trick. So what we do is we take data from our two hypotheses, or two different parameter values, and let's give them labels. Let's call one of them 0 and one of them 1. So theta 0 is label 0 and theta 1 is label 1. And what we can do is we build a classifier to classify data coming from these two different hypotheses, or two different parameter sets. And if we train it sufficiently well, you can show that the output of that classifier, the classifier will learn to predict what's on the right-hand side, 1 over 1 plus the inverse likelihood ratio. So that's sort of weird. Suddenly the likelihood ratio pops out, but nonetheless, it's to our great benefit, because what this is saying is we can train a classifier to try to separate two different types of data, two different data under two hypotheses. And from that, we can extract the likelihood ratio. For instance, taking the F over 1 minus F. But you get the idea where classification enables us to estimate now a likelihood ratio. And so you can sort of get this kind of picture where we sample data from these two different hypotheses from a simulator. So we get data under parameter set 1, data under parameter set 0. We train a classifier to separate them, and from that classifier we can estimate the likelihood ratio. The final step to this process, is that we can then take that approximate likelihood ratio. So here we have our simulator. We train our neural network to classify the different events, and that allows us to estimate a likelihood ratio that we can then feed into, for instance, a downstream frequentist inference engine. And from this likelihood ratio estimator, we can then go and do confidence interval estimation. And it's actually relatively cheap to do that because it's just evaluating a neural network over and over again. Now, what's really interesting here is that when we feed in the data here, it can be quite high dimensional. We can compute the likelihood ratio here for data that's high dimensional. And that's where we begin to gain power, because we're analyzing higher and higher dimensional data, using more information to understand this likelihood ratio and get a more powerful test statistic. And it can be quite powerful. Here's an example. Trying to look at estimating effective field theory parameters in the standard model, where in the middle here is the likelihood ratio as a function of the parameter value, and you can see the likelihood ratio in red is much tighter, and whereas trying to do the same inference on this parameter using histograms of data from these events is much wider. And so it turns out in this example, the idea would be that you could gain almost a factor of 2 in effective luminosity by using this high dimensional neural network over a 2-dimensional histogram. And you see the same on the right-hand side, where you're looking at now 2-dimensional confidence intervals, where the sort of widest intervals are this 2D histogram, but using high dimensional inference with these neural networks, we can get these green lines, which are much closer to the true values. In this case, it was an example where the true values were known. And this paper sort of documents a little bit more about what's happening there. So this is great. We can sort of think about using neural networks to estimate things like likelihood ratios to allow us to do high dimensional inference and sort of extract more from our data. But it turns out we can use neural networks and simulators to do more than just parameter inference. We can use it for things like exploring theory space. So in this case, often when we have many parameters, often we build a grid of different parameters we want to estimate. We want to see if we can rule out. But that can be very efficient. Often much of the region is either very far from the contour, for instance, the 95% confidence interval contour. These are X and Y axes here are different parameters of a model. So estimating anything in the bottom left or on the top is pretty much irrelevant because it's going to be very far to one side or the other in terms of confidence. What we really want is to estimate things really close to this boundary to get a very nice picture of the boundary. And so this was some nice work where you choose one theory point, test whether you've ruled it out, estimate the sort of the confidence you have at that point, and then you use a machine learning model to suggest a new point to pick and restart this process. So it's sort of an active learning process. As you accumulate more points, you can do a better job guessing where to pick the next point. And you get this sort of machine learning model, simulate new points, update your model, and then update the simulation, and you can sort of map out the boundaries here. And so that's a really nice way to help us begin to explore high-dimensional theory spaces without having to simulate all of them on a grid. Now, this idea of training a machine learning model to guide a simulator has also been used in ideas for things like detector design, where what you would do is what we did here is we want to try to optimize the design, for instance, of a magnet. This is a magnet from a multi-component magnet in the ship experiment, where we want to bend muons here away from some target area. And so one of the key tools that sort of drives machine learning development is the ability to do gradient-based optimization, but we can't take gradients of geont, we can't take gradients of our simulators, but we can build these surrogate models, these fast simulations we saw earlier in the talk. We can build surrogate models of a given detector. And if we parameterize it, if it's a function of its geometry, so it's trained for different geometries, then you can compute gradients with respect to the parameters and update it. So here's an example of a detector design being optimized step by step. Now at each step, you effectively train a neural network to emulate the current detector and nearby possible configurations. You estimate a gradient, you update your parameters, and you use the simulator to generate new data to train a new model. And it's sort of this iterative optimization that allows us to do sort of detector design. And now just, we started this discussion on detector design with the fact that geont is not differentiable. But it's not to say that there isn't the possibility that it could be. So perhaps instead of training surrogate models to emulator detectors, we could try to optimize the simulation itself. And this is some new work we're working on. This is still very new, but effectively, if we want to deal with or consider making something like GEONT or very complex simulators differentiable that we optimize directly, we have to deal with the fact that there's lots of discrete and discontinuous behaviors inside of these in these simulators. But there's been a lot of interesting new work on automatic differentiation, the way of computing derivatives of computer code from the ML world, that is actually getting better and better at understanding how to estimate derivatives of these programs with discrete randomness. So here's a sort of simulation, a toy simulation we built of a shower where there's these sort of discrete decisions about whether you interact and split into more particles when you're generating a shower. So naively, these would be non-differentiable, but with these new tools, we can actually build differentiable simulators and try to optimize detectors. So this is a toy example here where we fire particles into this detector, this weird toy detector, and there's showers that occur. And we want to optimize the inner radius of the detector so that the showers stop around a radius of 2. You can see the radius of the hits here in the middle as we're optimizing it, and the loss function that we can compute. And you can see that we're slowly moving our way down to the minimum of the loss function using these sort of more sophisticated derivatives of discrete programs with discrete random variables. So I think we're building towards having more and more interesting tools for things like detector design, which is something we haven't really been able to do in the past. This is sort of a new realm for AI, I think, in our community as we build up our knowledge. I'm not thinking here that we're going to be, having a neural network where we just say, design me a detector. That's sort of too broad and too hard. But certainly with experts giving rough designs, we can use these tools to help optimize detector designs with ML, sort of a human in the loop type process. And I think this will be quite interesting as we're thinking more and more about what is the next machine we want to build in collider physics. And then, of course, we need to design and optimize those detectors. So just sort of concluding a little bit, what does the future hold? We didn't sort of talk about the fact that there's a whole other cast of characters in the machine learning world now making a pretty big impact sort of community-wide. These very large models like ChatGPT, Stable Diffusion, Copilot, these kinds of tools can do really impressive things. Still amazed that you can type out some text and it'll generate a relatively realistic image. And so these are extremely powerful tools. However, I don't quite think they're going to be taking over the physics world yet. So here's an example where we can sort of, from some low-level text, some low-level description, we can generate high-dimensional data. From high-level concepts, we can generate low-dimensional data, but we don't quite get it right. Salmon in the river generating sushi in the river, or try to go to the other direction. If we were going to try to take high-dimensional data and analyze it, here putting a sticker of iPod on top of an apple cause the model to misclassify. And so these models are very powerful, but they can get things wrong. And a lot of what we know about physics is what helps us generate models that will avoid these kinds of mistakes in our world. I think it still begs the question, when we want to think about scaling models up, will that have as much of an impact on our community as it has, for instance, in language and vision? I think it's an interesting open question. Certainly, we could try to use these tools to aid us in things like writing code. There's an example from Lucas Henrik, a colleague of mine, who used GitHub Copilot to write Atlas code. That was pretty cool. And perhaps these tools can be used to help us write some of our other code in our community and make us more efficient in the process of doing data analysis. Nonetheless, we'll see what the future holds as we address the question of big models, and also address the question of physics in models. We've seen we're really gaining an understanding of how to design machine learning models and incorporate physics, and we can see how that compares with scaling up models and how we should think about designing the best models in the future, especially given that we don't have the same compute resources as industry. We can build more sophisticated systems these days, coupling together models or different components to achieve more complex tasks, and coupling together machine learning and simulators to do things like inference, but also address whole new challenges like how do we design a detector? I think that's quite a fun new avenue that we're exploring as a community. So with that, I think that sort of concludes my talk, and I'm happy to take questions. So thank you.
Yeah. So we have, oh, yes.
Hello. Yeah. Hi. Really nice talk. So I just had a small query in your LHC analysis example. I think it was page 45, and the algorithm's name was Rascal. What was the input that was there in that particular machine learning model?
Rascal.
Yeah.
Right. So so these models are, so I didn't really get into the, as you can tell, I glossed over a lot of the details. So this sort of simple picture of just comparing two hypotheses isn't exactly what we do. What's typically done actually is you take some reference null hypothesis and then you train that against multiple different parameter values. And what that's effectively going to do is what's called amortization. It's going to basically allow you to have a likelihood ratio that's a function of a parameter, of a theory parameter that you want to query. And now, since we have to tell this, basically you're telling the neural network, learn the likelihood ratio between some parameter value and some reference point, which is like the null hypothesis, usually. But now you have to, so the neural network can tune the likelihood ratio for each parameter value, but you have to tell it what the parameter value is. So the inputs here are the parameters and the observables at the same time.
So I mean, my query was rather because like it seems like the signature that you drew in that particular Feynman diagram is a VBF kind of a scenario.
Oh, sure. Yeah.
Yeah. So there actually what we found was that if we go to the low level calorimeter kind of thing, it improved a lot.
Oh, I see. That's interesting. No, I haven't seen that. I mean, in this work, it's pretty high level. I think it's more conceptual. I wasn't on this work, to be clear, but I think it's this sort of high level conceptual that you can, instead of comparing to a 2D histogram, you can sort of feed in all the 4 vectors to do the inference on these parameter values. So I could certainly believe you that when you look at more realistic data, that exactly what you feed into the neural network, whether be it 4 vectors or calorimeter clusters or jets, that can make a pretty big difference.
Thank you. Mm-hmm.
Hello.
Hello.
Yeah, very nice talk, and touched upon many things which were covered in the school, including what were taught in this afternoon. To your slide 49.
Oh, yeah.
Yes, so if you could, so we learned a little bit about differential programming this weekend, but if you could elaborate a bit more as to what's the input and what's being generated here.
Right. So here we're, what we do is, the way the simulator works is we run the simulator, a particle goes into the detector and it showers. And we can get the location of the hits of the shower on the detector. The detector are the gray regions. And we're trying to optimize the inner radius of the detector, so only one parameter. So you can see for a given shower, these are the hits in the middle. And what we're trying to basically optimize is that the average hit radius is, I think, a value of 2. It was just sort of chosen, as an example. And what you can do is, for any given value of the inner detector radius, you could, for instance, run a bunch of showers and compute the inner, you could compute the average hit radius and the loss function, and that's what this loss is. The question, though, is, typically in machine learning, we're thinking about taking given examples of data. So simulating a shower, using that to estimate a gradient, using things like automatic differentiation, and specifically Monte Carlo gradient estimation. So from like a given shower simulation, could we estimate a gradient and update the parameters so that we simulate slightly differently next time? So in this case, we change the radius a little bit and then run another shower. And it turns out there are ways, so typically there are several ways that you can compute gradients of these sort of programs that, or probability distributions, if you will, that have discreteness in them. I don't know if you want me to talk about that in more detail, but effectively we're using some sort of very new ideas in automatic differentiation that allows you to sort of compute derivatives even of these discrete processes where we're sort of making discrete decisions at each of these steps along the splitting process, where we can compute a gradient contribution and propagate it to the next step to still get something that looks like a chain rule, so that we can automatically estimate these gradients in a computer. But maybe that wasn't the question you asked.
No, that answers probably more details would have been interesting, but I guess time is a constraint here. Okay. We wish that you could be here, but another on GAN, GAN or generative models replacing GAN4. Sure. So maybe this is a naive question. So it's still, this process still as a starting point takes GAN generated events as a starting point, or the idea is in future you won't need any of the cross-section information, a lot of cross-section information that goes inside GAN, and that will replace that process.
Right, that's right. So eventually you would, when you're simulating events, instead of running GAN, what you do is run this neural network simulator. But I think we will never, completely get rid of GAN. And the reason is that you need GAN to develop your training data. The difference is, the hope is that you can sort of generate training data for low-level things, like generate training data so that you can learn how to simulate individual showers. And then an event is composed of lots of showers. So so we can get 100 million particle showers, we can simulate that. But once you've learned the shape of a particle shower, then you can use that many, many times to simulate events, because every single collision may need 100 or 1,000 particle showers to simulate. And so you sort of hope that you can sort of pre-simulate lots of GAN stuff, but enough that you can learn these low-level simulation details. And then you sort of have a combinatoric benefit of combining the simulator for each shower. You can combine lots of those showers and start to describe many, many different kinds of events. But in the sense that we always need GAN for training data, most likely, although maybe someone will come up with an unsupervised learning way to build a shower generator directly from our real data. But until then, we will always need GAN to train the models. So it's still guiding the process. It's just that when we want to eventually simulate lots of data, we want to be able to do it faster.
Yeah, so there are no more questions. Then let's thank Michael once more.
Thank you.